How's everyone doing? Good. Still got my big blue bubbles in my chat window. I think that's okay. All right, cool. So let's start with questions. I only have one person in office hours yesterday, which is amazing because I had several people who contacted me for advising and none of them showed up, and one person came in from class. So we're definitely in the end game here. But keep bringing questions if you have them. All right. Well, let's keep going down the process track, and I'm tentatively planning to finish talking about processes today. So I want to talk about two-way communication between processes using a pair of pipes, and then talk about duplicating standard in, standard out to connect the I/O of an external command to a pair of pipes, and then I'll make a few comments about bidirectional communication. And this is stuff that we will probably encounter in a more in a deeper way in CSE223 when we get into networking and talk about doing networked communication between processes. But we'll do a once over of it today. And then tomorrow I want to go back. We never did get around to talking about awk for real, so I want to spend a day going through awk and just making sure you've seen some of the basic constructs for awk programs. And then Thursday, I'd like to go back and do some practice problems on grep as a class, because we talked about regular expressions and I posted some practice problems, but we haven't really talked about them. So I want to make sure people are comfortable with regular expressions, even though everybody used them in homework 8, right? I want to make sure you're up to speed on it. So I'm planning on that for Thursday. And then Friday we can spend, just kind of doing a quick 40-minute overview of 11 weeks of material. And that would be the end of the course. So a reminder, because I'm still getting questions, your final exam is Monday at 10 o'clock on Canvas. And it's Monday from 10 o'clock to 11:50. I'm not really sure how to study the recent topics for the final. Are we supposed to understand the definitions and implement programs? So I will not ask you to implement programs with fork and exec and pipe and all of that stuff. But I want you to have seen these things, and I could ask, some high-level conceptual questions. Describe in one sentence the main reason for a fork, or the main behavior of it, or what does the return value from fork tell you, or something like that. It's I can't say none of this will be on the exam, because then my attendance will drop to 0, or close to 0. But we haven't had ODPs or programming assignments or homework questions on this stuff, so if I asked you something, it's going to be, pretty high level conceptual question. So don't stress over the process stuff, but I would like you to keep coming to class. How's that for an answer? All right, well, I need glasses. All right, cool. So where did we leave off? Okay, this is a good place to continue. So here's what I'm after. Let's have a main process which starts off and creates a pair of pipes. Now, a pipe is just a pipe. You write into one end, you read from the other end. But I'm going to think of this first pipe as something I write into, and the second pipe is something that I read from. All right. This is not so much about the mechanics of pipes and process creation as it is sort of keeping track of what we're doing. Okay, so this is an organizational challenge more than a technology challenge. So I'm going to have a pair of pipes, and I'm going to call this pipe to child. I'm going to call this pipe from child. All right, and I'm going to set those pipes up, and then I'm going to make a call to fork, which will give me a clone process. And my whole goal here is I'm going to create an entirely separate process which will convert things to uppercase for me. Okay, so I'm going to have, the user input a string here, and then I'm going to send that string to my child process, and the child's going to convert it to an uppercase string and send it back to me, and I'm going to print it out. Okay, this is a goofy thing to do, but it's a basic client-server model, right? Which is really what most of the web is. Clients are things like, PuTTY or a web browser, and servers are things like, the secure shell daemon that's running on our Linux machine that lets us log in, or the web page server sitting on port 8080 that feeds you web pages, or the print server that sends your jobs to a physical printer. So this client-server model is something that we'll deal with a lot. And I'm going to basically think of my original main program as a client, and the child that I'm creating is going to be a server. And I'm not going to do execs or anything like that. I'm just going to have, different code inside my one main.c that can act as either the client or the server. But the point of this exercise is to establish two-way communication between a client and a server. All right, so so there's a long punchline. Two-way communication with a child process using a pair of pipes. All right, so the main thing, like I said, is going to be sort of keeping track of what we're doing. So my pipes are basically a pair of integers, right? So I'm going to have, a two-element integer array. And again, I'm going to have one called toChild and one called fromChild. The parent, right, who I'm thinking of as the client, is going to write into the toChild and read from the fromChild. But the child, which is the server, is going to read from the toChild and write to the fromChild. Okay, so you see where this can get confusing, right? And there's about an 80% chance that I won't get confused today, which of course means, a 20% chance I will. So let's try this. And I don't know how I'm going to prototype my functions yet, so I'm just going to leave these blank for now. But it's essential that I create these pipes before I fork, right? If I create these pipes down here after I've already forked, then the server doesn't have access to those. So anything that I create before the fork is available to both the parent and the child process. Okay, this is a shared memory concept, right? These things are structures that are managed through, manipulation of memory locations, and even though these are separate processes, they'll be touching the same memory locations effectively. Alright, so let's make a pair of pipes. So let's make a pair of pipes, integer to child, send from the parent to the child, and then from child, receive from the child to the parent, and then we have to actually make the pipes. Alright, so those calls to pipe, you know, we should check the return status. And this is something that I'm going to be pretty relaxed about in this course, but in future courses, you know, you would get major deductions for not doing this. But generally, any time that we call, you know, a function, we should probably be checking to see whether that function succeeded. Now, if we're saying printf, we don't have to check the return value on that. We know printf is going to work, right? Or something, you know, majorly catastrophic has happened. But trying to create a pipe, we're using resources that may or may not be available, right? There's only so many pipes that can be created. So technically, you know, every time that I call this function, I should check the return value and make sure that it returns a 0. And if it returns, you know, -1, then something went wrong and I should print a message and proceed accordingly. But I'm never going to do that in here if I'm pretty sure this is going to work. So we're just going to confidently assume we've made a pair of pipes. I'm not going to bother printing them out. But here I'm going to fork, so I'm going to say create a clone. Alright, if the fork returned to 0, it means I am the cloned process. And so I'm going to call something called child. And I'm going to need the child to have access to both of these pipes. So I'm going to pass both of those as arguments. So I'm going to pass to child and from child. Otherwise, if we got a non-zero PID, I'll call my parent code. Alright, so now I know how to prototype my functions. So I'll pass a pair of integers. Alright, so let's write these things. And these are to child and from child. Alright, so let's think about these pipelines, and we got this, well, I got this backwards yesterday, not we, my bad. If this is, you know, set up with a file descriptor, we write into FD bracket 1, and we read from FD bracket 0. Okay, this corresponds to what we think of as standard in. So the parent process is going to write into this end of to child. It's going to read from this end of from child. It's never going to do anything with that end of this pipe or that end of that pipe. Okay, it's going to write into here, read from here. It's not going to do anything with these. And the child process, on the other hand, is going to write into here, read from here. It's never going to do anything with these ends. All right. So to hopefully avoid creating too many zombies, first thing we're going to do in the parent process is close the ends of the pipe that we don't want. And if I get these wrong, everything will cease to work. So the parent is going to write into toChild bracket 1 and read from child bracket 0. So I'm going to put some comments in here. So write into toChild bracket 1, read from child bracket 0. All right, so we'll close the ends that we don't need. When we open with an open, we write with a write, read with a read, we close with a close. So we're just going to say close toChild bracket 0. Again, you know, we should probably check the return status from this. I'm not going to worry about that. And close from child bracket 1. All right, so remember our goal. We're going to let the user type stuff into the parent process. It's going to send it to the child. The child's going to convert it to uppercase and then send it back to us. All right, so we'll say enter something. We'll do our usual fgets loop to read a line of input. And so I'll put a character array up there. Okay, so what do we want to write? Well, we want to write into toChild bracket 1. So that's the file descriptor we're writing into. And the string we want to send in is buffer. And then how many characters do we want to send? So if we say HELLO, that's 5 characters. We also want to add a null terminator on the end. We don't have to. We don't have to send null terminated strings. But if we don't do that, then we have to add the null terminator on the receiving side. So we're going to make things a little easier on ourselves. We're just going to send out string length of buffer plus 1. And the thing to remember here is if buffer is not null terminated, I can't use string length to see how many characters are in it. Yeah, I will make this code available on Canvas. I was just thinking that. Alright, so string length only works with a null terminated string. So if I send it without a null terminator, I can't use string length on the receiving end. Alright, so we'll add that extra null terminator. And, you know, I should be checking to make sure that I didn't read in, you know, too many characters and so on. Alright, so we'll write that out. And then we're going to read back the response. So read back the response from child, which should be an uppercased version of our text. So I'm going to call read. So I'll have an integer called amount read equals read. And I read from, what did we say up here? We're reading from child bracket 0. And we will read into our buffer. And we'll read up to 120 characters. So when we write, this last argument says how many bytes should we push into the pipe. When we read, it says what's the maximum number of bytes that I'm allowed to take in from the pipe. And, you know, unless we're guaranteed that this ends with a null terminator, we could end up with an unterminated string. So we would want to, you know, typically check to see if we read in a full 120 characters, and if we did, make sure that we terminate the string. Details you'll have plenty of time to deal with in another year or two. All right, so there's the amount read, and I'm going to assume it's null terminated, so I'm just going to go ahead and say we'll just just print out the buffer that we received. And then we'll go ahead and prompt the user again. And that's the end of our loop. And then we'll just return from the parent process after the user hits Control D, and we'll exit out. Now I should close my other file descriptors, but I'm not going to. Yeah, I will. I'll be nice and clean about this. So I'll close to child 1 and I'll close from child 0. Alright, there's our parent process. It's not going to do anything unless there's a child process to pick up the other side. So, so let's do that. Okay, so I'm the child, so we're going to write into toChild 0. Nope, going to write into from child, we're going to read from toChild. Alright, so child process over here, it's going to read from the toChild pipe, it's going to write to the from child pipe. And we always read from, index element 0, we always write into index element 1. So we should be reading from toChild bracket 0, right? So that's this one right here, and then we write into from child bracket 1. And maybe it's just me, this is the hardest part of the whole process, is getting this stuff squared away, right? So, I've been doing this for 30 some years. I still need to start with a picture. And refer back to it until I find a pattern, and then once I've got the pattern, I can sort of fake it from there. Alright, so here's the child that's going to read from, and we're reading from toChild bracket 0. We'll load it into this character array 120. We're not going to bother printing it out, but let's convert it to uppercase. So, so do you know about 2upper? So 2upper comes out of C-type. It's one of a bunch of useful functions. They're actually macros. 2upper will take a character and return the uppercase version of it. 2lower returns the lowercase version of it. And if you include C-type, you get a whole bunch of these things available to you. So there's, is alphanumeric, is alpha, is control, is digit, is lower, is punctuation, all of these cool functions that you can use. You never want to compare ASCII codes in C, right? That's not guaranteed to be portable, and it's not guaranteed to work down the road. If we switch, from the ASCII character set to some new character set, right? Or if we start using Unicode and such, these functions will be updated, and when you rebuild your code, right, you say make to recompile and relink everything, these things will still work. Whereas if you say if ASCII code's bigger than or equal to 65, less than or equal to 97, that's only working for today, for ASCII in the US. So all of these things are available to us. So we'll apply off of those. And we'll pull in C-type. And I don't think it's camel cased, I think it's just 2upper. Alright, so, and if you give it something that's not a lowercase letter, or something that's not a letter at all, then it just returns what you gave it. So if I have a digit and I call it, run it through 2upper, I just get back the original digit. So this is safe. It's not just blindly, subtracting 32 or something. So I'll go through each of the characters that I got from the parent and take those characters one by one, run it through 2upper, and save the result in buffer. So we'll save it to uppercase. And then we'll send it back to the parent. So this is just a write statement. and we're the child, so we write into from child bracket 1. We're going to write buffer, and how many things should we write out? Exactly the same number that we read. So just result. Alright, the other thing that's missing is this needs to go in some kind of loop, because right now the child's going to read once and then it's going to exit. But let's go ahead and compile this and fix our error so far. Yeah, that's not too bad. My formatting is all weird today. And these spaces don't matter at all. They don't matter to the compiler. But you know, even if you're just writing junk code, it's nice to have a consistent formatting, so that if you're going back and you're looking for, you know, issues in your code, things that are unexpected will jump out. All right. Now this is always fun when you fix an error and you end up with like more errors as a result. So let me add string.h, and then we'll fix those syntax errors. All right. So line 53. And this is one of the harder errors to find, except that I do it a lot. So it jumps out at me pretty quickly. It's not as bad as the single equal versus double equal, but that stray semicolon turns this line of code into a function prototype, and then that curly bracket is meaningless to the compiler. So, alright, shockingly. Let's go ahead and run this. So it says enter something, and I can say hello there. And it comes back with uppercase hello there. And then I'll say crash time, and you know, something happened, right? Alright, I have no processes out there. So let's run that again, and let me open up another window. And I got too many processes here. All right, but here's the interesting part. I have two E3 processes running. All right, so E3 was the main program that I started. This second, this first E3 process ID 18919, is the parent of this second one. So this highlighted line, that's the child process, okay? And the first one is the main program. So if I type hello and I hit enter, I got back my result. If I do my PS again, my parent process, 18919, my main program is still there. My child has exited, okay? It's still listed in the process table, but it's defunct. And even better, it's a zombie. Okay, the process exited because, you know, there's no loop in that child function. It read from the pipe, converted, sent to the pipe, hit the closing curly bracket, returned, exited from the main program. So the program is finished, but it hasn't gone away yet because it's using resources that are still being consumed by the parent. All right, so this is a zombie process. But if I try to send something to it, right, my main program will exit. All right. So let's see. Let's put the child in the loop. Alright, so when we try to read from a connection that's been closed, we should come back with a 0. Let's double check that. So on success, the number of bytes is returned 0 indicates end of file. Alright, so I could check to see if it's less than or equal to 0. I'm going to have faith and just say 0. So while result is not equal to 0, I'll convert to uppercase, I'll send it back, and then I'll go ahead and do another read. Alright, so that's just a loopy version of what we had before, where I'm doing one read outside the loop, check the return status. If it succeeds, go ahead and process it, and then at the bottom of the loop, go ahead and read the next line from the parent. And keep going until we get to the end where we exit out of the loop. And at this point we can assume the parent exited, and so let's shut things down ourselves. And so let's close out the pipes that we don't need, and we forgot to close these in the beginning. So I'm going to close to child bracket 0 and from child bracket 1. And in the beginning here, let's close the ends that we're not using. Alright, so now we got a good old mess, and you know, if you walk away and come back to this, it's all going to look the same. And so, you know, you want something that doesn't look like code to help you figure out what's going on. Alright, so let's go ahead and run this, and let's take a look at our PS over here. Alright, I've got two E3s running. So that's good news. I'll say hello, and I got back what I wanted, and I still have two E3s running. This is a test. Ha ha ha, it works. Alright, so this is a basic client-server model we've got now. Theoretically, when I hit a Control D over here on the parent side, right, my parent should exit, and the child exited also. Why did the child exit? Because it was sitting in a loop which said read from the pipe, and when the parent exited, the end that the parent was writing into got closed, which tells anything that was trying to read from the pipe, hey, you're not going to be able to read anything because you're at the end of the file, the end of the input. And so the read came back in the child process with a 0 saying end of file, and that caused the child to exit. Alright, so this is, you know, fairly hairy looking, right, even with some comments. But it's really, it's a simple, you know, mechanism that's being set up, just a pair of pipes. This fork writes into that, reads from that. This fork reads from that, writes into that, right? But in C, it's kind of, you know, involved setting this up. In other languages, this is a lot easier, right? In Java, this is pretty trivial. Doing something like this for inter-process communication. But, you know, all these other languages that do this stuff that, you know, you just draw a smiley face and now you're talking to another process, right? It's using all of the stuff underneath, right? This is the close to the metal implementation of those higher level mechanisms. So I'm absolutely not going to ask you to do anything about this or understand this or you know, answer questions about it on the exam. But like I say, in probably 223, when we're doing Java, we'll be playing around with networking, and we'll come back to this. And then in later courses at a university, you'll spend lots of time writing code similar to this. But yeah, I think it's interesting too. I mean, it's kind of cool to take a peek under the hood, you know, and see what's actually going on in there. And this gets you closer to, you know, the actual what's going on. You can go deeper than this, right, and start seeing how this interacts with the operating system, and then you're really, you know, down to the gory details. And that would be like an OS course, or maybe a computer architecture course. But this is something that we'll actually use sometimes. And it can be useful. I was going to pull this up ahead of time, and I don't know if I can find it. So I don't know if any of you have looked around my YouTube channel outside of class, but I have a channel on Minecraft, and a bunch of videos on there that are basically built around the idea of driving a Minecraft server using the same setup, right? Just using pipes to send commands to another process. And it basically, you know, fork off a child who starts running the Minecraft server, but it lets me send commands to it, and so instead of doing a mod on the server itself, I'm just using a plain old generic Minecraft server, but I can write C code that sends commands to the server and picks things up from the server. And so, you know, I can create objects and move them around and read blocks and rotate them and scale them and things like that, and it's all done just, you know, with a pair of pipes, you know, with a server and a client basically, and just sending commands out. And it's you know, a general model, right? The whole idea of programming is if you can do something manually, there's a good chance that you can get a computer to do it for you more easily, right? Less labor for you, fewer errors, and so on. And so this is just kind of an example of that. And so here's my exec, you know, and we're going to talk about dupes next. But it's basically the same stuff that we're doing with, you know, this basic client-server model. Yay, Chicken Godzilla, yeah. I made a giant chicken that goes around and destroys blocks and spews lava just for fun, and does excavating for me, basically. So, all right, so let's see. So what are we up to? E3. Well, let me switch to some pre-existing code here. All right, so this is great if we're creating both processes that are communicating, right? So I'm making a server and I'm making a client, and I'm going to have them interact. We can use pipes. But a more common situation is, you know, like the Minecraft server example, where this side of things is going to be running something different, a different program, right? For example, it might run, you know, /bin/basic calculator, or it might run the Minecraft server that lets me type in server commands and so on. So if this is a separate process, right, we're going to use some kind of exec, like execl, to turn this clone of the original process into this new process, right? That's what we were looking at yesterday. But we can still maintain this two-way communication with this new process because these file descriptors are preserved through the exec. Okay, and this is kind of a quirky thing. When we exec, remember, our essence is changed into the essence of a new executable program. But any file information that we've already set up persists through that transformation. Right, so walking down the street and you pull your brain out and put someone else's brain in, but you still have the same eyes, right? So you're still seeing the same things that you were seeing before that transformation happened. That's how these pipes basically work. So there's one other function that's really useful, and that's called dupe2. And dupe2 is a way to basically replicate a file descriptor, right, in our case the end of a pipe, but have it turn into something else. Alright, so this is going to get increasingly hand-wavy for the next few minutes, and then we're done. But remember, when you have a process, you always have standard in, standard out, and standard error. I'm not going to worry about standard error. Standard in is file descriptor 0, standard out is file descriptor 1. And I'm creating pipes, and I have, FD1, FD0 over here. These are, different numbers, like 4 and 3, for example. What we can do is, before we switch to being another process by calling it exec, we can call dupe2. And dupe2 will do the following. It will say, take this end of the pipe and copy it, right? Make a new thing that we can read from. But instead of giving it a new number, give it the number 0. And once we do that, anything that tries to read from standard in, fgets for example, or getC, getcar, when it says, okay, I want to read from standard in, where's standard in? It's going to say standard in is, file descriptor 0, but file descriptor 0 is actually connected to this end of the pipe now. So we can set up a child process so that when it reads from standard in, it's actually reading from this. And when it writes to standard out, it's actually writing into here. And now we've got a process running that's communicating with our original process just like our own server was, right? Reading from this end of the pipe, writing to that end of the pipe, which means that the main process can write into here, read from here, and be communicating with standard in, standard out of this new process. So yeah, it changes standard in to effectively a location in memory. I mean, it's always a location in memory, but it changes standard in to a location in memory that refers to this end of the pipe instead of, the keyboard or, input from a file or something like that. So yeah, that's a good way to think of it. So let's see. All right. So here's some code I already wrote to play around with this. So I'm setting up some defines for in and out, right? 0 is always standard in, 1 is always standard out, but I didn't want to have to remember that. So I'm just going to make a symbol in, which means 0, out, which means 1, and I'll use those throughout here. Here's the main program, here's my pair of pipes. Okay, same convention as before, some temporary variables. Make a pair of pipes, call a fork. If the fork returns 0, I'm going to call the child process. Otherwise, I'm just going to write the parent code in here. All right, and there's a comment here which is we'll never actually come back from the call to the child. because inside the child code we're going to morph into another process. We're going to morph into the basic calculator program. All right, so what's the parent going to do? Exactly the same thing that we were doing before. Okay, we're going to read a line of input from the user. We're going to write that out to the child. Okay, I don't seem to be putting a null terminator on, but I think I'm okay with that. Because I'm not trying to pass a null terminated string to BC. I'm just trying to pass characters like what I would be typing in. So I'll write that out, and then I'll read from the child up to 120 characters. And here I'm going to take what I read back and I'm going to put a null terminator on it. Okay, so bytes is going to tell me how many characters of output I got. And you know, when BC types out a result like 4, it'll type out a 4 and a new line. It doesn't type out a null terminator at the end, right? It just, you know, outputs the characters that I see. But since I want to use that in a printf statement, I'm adding a null terminator myself. All right, without that you get weird stuff and then eventually a seg fault. All right, so this is just going to be a loop. Read from the user, send that to the child, read back from the child, and print out what you read. And then when I'm done, my parent will just exit. So that's the end of my function. And I'm shamelessly not doing any house cleaning in here. The child process is trivial, other than, you know, these incredibly heavy-handed functions. So first I'm going to close the ends of the pipe I don't need. And then I'm going to do a pair of dupe2 calls. So dupe2, this is going to say, let's take the two child bracket in. Okay, so that's two child bracket 0, which is, you know, this end of the pipe. And let's make a copy of it and call that copy file descriptor standard in file no, which is just a symbol for 0. Okay, so this is doing this part. It's saying let's take this end of the pipe and let's number that as file descriptor 0. So from that point on, whenever BC tries to read from standard in, it'll be reading from the pipe. And then I take the output side and I set that equal to file descriptor 1. So here's my ASCII art, right? To child bracket out feeds into basically standard in of BC. And standard out from BC reads into from child bracket in, right? Which is, you know, what's being written to and read from in my main process. And then I do my execl. So I call user bin BC, and that runs the BC program, and I never move beyond that in this code. Alright, so let's go ahead and compile that. I'm going to ignore all of my warnings, because it's ignore warning Tuesday. And let's go ahead and run, and let's make sure it's /BC. So enter an expression. Right. So there's a couple of processes running. There's /BC. That's the program that I ran by saying /BC. Yeah, every Tuesday is Ignore Warning Tuesday. Didn't I mention that in the beginning of the quarter? And this process 171 created a new process 172, which is actually running, you know, the system BC command. So if I type in something like, you know, 2 + 2, it tells me it received a 4. Right? And that's you know, arguably no more exciting than just doing this. But it's actually way more exciting because, you know, this came into my C program. This came into a character array, which I could, you know, do different things with. I could take that, I could append a *2 on the end of it and send it back to the server, the child, and it would send me back a string containing 8. And then I could append a *2 on the end of that and send that to the server, and it would send back a 16, right? And I could have something that generates, you know, a table of powers of 2 using BC as, you know, a server process to do the heavy lifting for me, to do the arithmetic string manipulation. And that's kind of cool. This will only work up to 120 characters, but you get the idea. And then when I exit, right, I Control-D the main program, which, you know, said end of file. And if I look over here, My BC and my child BC processes are both gone, so I didn't create any zombies. Usually zombies are hard to avoid. All right, that's a huge, swath through the space of processes with a breakneck pace. But just kind of first glance at it if you haven't seen this before. So tomorrow, let's go back and revisit awk and dig into some awk programming for doing some file processing, and then we'll go on to regular expressions, and then we'll wrap up the course on Friday. All right, thanks. I'll post this code on Canvas. Have a good one. We'll see you tomorrow.